The third part, let's say the fourth one. Which is a linear accelerator relative to one initial frame in this is relative now. Is locally identical to a frame and raised in a gravitational field. This actually gravitational is uniform. Here again, you see there's another word locally. This is the same meaning like what I just said in P3. This is local. The locally, this is what I'm going to draw a picture with you is local. So, for example, we are in the elevator, so there is no gravity. But my elevator is uniformly accelerating along this direction, right? This is a constant. In this case, when this acre person through this acre, the chuck will fall down, right? Because my elevator is uniform accelerating in this direction. This will fall down with the acceleration exactly this acre in this direction. A equal minus mg, right? So this acre will mg. This is a g direction, right? So this acre not gravity. My elevator is uniform with actually constant acceleration actually going up. Then now if I release one ball, this ball will actually falling to the ground with a negative acceleration. This actually go minus mg, right? You notice. So, but this is also the same now. If I have an elevator here, I have a person here, but now I have Earth. One simple example. We know this actually, because of a shortcut, this guy is also accelerated down, right? So again, this is a constant acceleration. Then you cannot distinguish these two, right? So because this acre uniformly accelerating, this is no gravity. I have not a uniform stay here and rest, but my Earth has a attractive force. This ball also same moving to the ground with the same trajectory. So you cannot distinguish them. Again, there is a keyword here, local. So when I say local, exactly the meaning I just explained. Not locally, I can use the identification to tell the difference. Okay? So this acre is the part we have. Any question about this part? Okay. Now, from this actually, I'm going to introduce three masses. Actually, try to put this actually expressly into the mathematical formula so we can really test. Okay? So this actually comes from, let's say, for the P1 part. For the P1 part, we can, let's say, a particle with an initial mass m particle 1, I means the initial mass. Then we have particle 2, also with an initial mass. So if I have a gravitational field, which can be time dependent, then you can see my actually, this is for 1, M1 with an initial one, let's say fell down. I have also the particle M2, I fell down with this one, right? But each of them also have the positive mass, which means that, for example, when we have, let's say, F equal A M, this M should be inertial mass, right? But if this guy is in a gravitational field, this field some gravitational force, when we consider F equal M1, M2, R squares. This one is a positive mass, right? This means like if I put them how they attract each other, you can imagine this mass will be different from this one. This is F equal AM, this is initial mass. How when I move this table, try to push this one, what's the resistance of this guy, right? Now this mass, when I put this ball in gravitational field, how this mass fills the gravitational field. So this one we normally call positive mass, but they can be different, right? So this anchor is a case. So that's why I have two balls. I have this anchor with M1, initial mass, positive mass. They are moving in the gravitational field. So I'm going to use Newtonian laws. This one and this one. Why do I use Newtonian laws for this principle? When I'm talking about Einstein's theory, because it contradicts on that. Newtonian law always certified this principle, right? So there's no difference. So that's why, that's what I said before. The equivalent principle hold also in Newtonian gravity. Of course, Einstein's theory always hold. If you disprove this principle, you disprove Einstein's theory, meantime you also disprove Newtonian theory, right? You also disprove other theories which use this principle. So that's why this principle is certified by Newtonian gravity and also by Einstein's. Okay. So here we can talk about Newtonian gravity. Use this, no problem. So then, according to this anchor law, we have this anchor, let's say F1 equal minus M1P, the gradient is phi, right? F2 equal minus M2P multiply the gradient phi, right? This is the forces, the two balls were filled. Then this is from this is actually first law, right? This is actually Newtonian gravity, R squared. Because you have actually constant, I didn't forget this constant. So we also have F1 equal A1 M1, right? F2 equal A2 M2. So this is actually Newtonian gravity, this is actually second law of Newtonian mechanics. So if I combine this together, I'm going to get actually M1 sorry. A1 equal minus M1P, gradient is phi, and M2I A2 equal minus M2P, correct? So what I calculated is, when he actually in the beside tower, if he draw actually a hammer, and it feels if there is no air, he can go, these two guys are equal, right? So if these two guys are equal, this is equal, right? This over this one equal this over this one. You see, now I'm purely using Newtonian gravity. Why? Because Newtonian gravity also this principle holding Newtonian gravity. So Einstein just borrowed this principle from Newtonian theory. So then I have actually M1I over M2I equal M1P over M2P. If you have many particles, you can have actually all of them should be equal. IP, sorry, 2. Oh, sorry, M1. So I have actually M1P over M plus 1. So this is actually, there is no difference. Okay? So this actually, the calculus actually experiment tells these two guys are equal. Then the initial mass and this will be, what I'm doing this. This will be M1P, M2I, M2P, right? So M1P. So they are actually the same. So then you can say, by proper choose unit, I can always put them equal 1. So this is two guys are equal. This means that initial mass equal positive gravitational mass. This is called positive gravitational mass. This is actually measure how much this actually the properties field gravitational field, right? This is actually how to resist it when push the table to accelerate. So this is two mass in principle, they are equal, but by using calculus experiment, I can prove they are proportional. So this is actually the sense I have this one. Okay? We have actually certain mass. When I wrote in here, actually I already put a M1P equal M1A. What's that mean?
Independent of mass.
Yeah. Okay. This is where equal Phi1 equal minus R M1. This is the gravitational field produced by this mass. So this is actually how the particle field. This is the stress produced in the mass. So when I wrote here, actually I didn't distinguish this two. Because you actually one produces field, another field. Another produces field, another field. So this actually uses similar argument. What I want to see, this guy, M1P, is the world, M2A, M2P. So they were equal too. Okay? So because of the time, actually, what I have introduced here, I have introduced three different masses. If the particle has a mass, this particle will produce gravitational field. This is called gravitational actual mass. This is measure the stress of the gravitational field. This is produced by this mass. So there's also one side produce a mass, a gravitational field. You will feel the gravitational field. So you also have M2P. So using this argument, I'm going to say this is free mass will be the same. The gravitational positive mass and the gravitational actual mass and the initial mass, all of this are the same. This Newtonian principle, this is all of the Einstein principle of equivalence. This actually is the three masses that are equal. According to Newtonian gravity, according to Einstein gravity. So, this is true or not? We do not know. But so far, no single experiment tells us this is not true. So the most recent experiment tells us this is true. So far, we have no any evidence it is not true. Okay? So there is if I want to like you take from here that there are three different masses. Gravitational attractive mass, we shall measure the gravitational, the strength of this particle produce the gravitational field. And then a gravitational positive mass, which describes how this particle feel in the gravitational field. Then also initial mass, when I push this particle, accelerated particle was the inertial mass. This is three masses. Actually, in Einstein's theory, Newtonian theory, they are equal. So this is a principle. We do not know if it's true or not. So we are still testifying. So far, all the experimental tells us this is true. Okay? So I think perhaps we stop here. Okay? Yeah.
Thank you so much.
Oh, yeah. Yeah, this will okay, sorry.
10 minutes. Change if you want.
If you want anything in your application mentioned in your value,
Badges, please write.
mention
Okay.
Are you coming back? So we will continue. I think this lecture will be more mathematics. So I use this part using geodesic relations. And getting used to this even from the very beginning. Later on we define, let's say, the gravitational waves, we still use the geodesic relations. Like what I said, you can imagine if we consider my two arms. This is a particle, this is made of particle, this is made of another particle. So these two particles were sitting there actually moving on geodesic test particle, right? So we want to see what's the difference between this, the distance between these two particles. This is exactly, I emphasize local mean. So local is nearby. So when the gravitational passes through this, they will change the geodesic deviation exactly measure the difference between the two particles. Of course, we have many infinite particles in this arm, infinite particles in this arm. You should consider both of them. That's why then you consider a circle. This two arms will pass to one circle. You want to see what's the change, the distance between two arms. So gravitational will exactly stretch one arm and squeeze another. This is a unique characteristic of gravitational waves. All the other waves will uniformly make the circle shrink. So that's why you cannot measure the distance, the difference between the two arms, because they always either stretch uniformly or contract uniformly. Because the gravitational mass is always positive, actually, and always contracts. Okay? So this actually, now I'm going to actually first consider the Newtonian derivations. Then from the Newtonian derivative, we will motivate actually to write down the Einstein equation. From this side, the first set, you can see how Einstein were starting from Newtonian gravity gradually generate relativity. So this is the logic. So our second lecture will be Einstein field equation. So the first part we will work on So let's consider motion of two particles in the Cartesian coordinates. We use x, y. So this actually the coordinates. So I use actually xa equal x1, x2, x3. This is equal x, y, z. So we just use this. So then we use the method d sigma squared equal dx squared plus dy squared plus dz squared. This you can also write as d ab dxa dxb. Now ab actually goes from AB equal 1, 2, 3. So here, so this actually allows me to write AB equal 1, 1, 1, 0, 0. So this is actually our starting point in Newtonian gravity. So if we let's consider particles. Let's say one is on this direction, we call C1, another one called C2. So let's say this is actually on the t equal, on time t, this is actually C1 on the point P, this is C2 on the point Q, right? So this is actually the two parts. We want to see what's happening. This is actually the difference between the two geodesics. So we are assuming let's see, the C1 is x at and C2 actually x at plus eta at. So here I call this eta. Of course, this also depends on time t, because this is the same time, right? As you can see, this is the same time. So we are assuming there is actually a gravitational field. We use the phi and time x. So here, my expression x means a vector. Sometimes I use a vector simply just xt. So this means xt, t, x, y, z. Okay? Then you can see, according to Newtonian gravity, we have, let's say, x double dot at. Dot means dx dt. So I use double dot means second derivative. This equals acceleration equal, if I put in the mass, each of them, m1 equal 1, m2 equal 1. So this actually, I simply have minus GAD, because this is the index of I just simply d phi dx d. So this is on the point P, right? So for the simplest, I just simply run this like a dA phi, let's see, on the point P. Okay, so this is my partial derivative with aegis R. So this anchor for the particle C1, then you can simply see for the C2 anchor equal x double A plus eta double A. This anchor, because this anchor x A plus eta P, this will be equal minus AB d phi dxb, but now I'm point Q. So I just simply, this is equal minus d a phi q. So this actually the expression. So if you have any question, please raise your hand, let me know. So now, you see, I'm going to expand this guy. Because this actually will d a phi and q. Q actually equal d a phi. So this actually is x plus eta, right? So this is eta is a very small quantity. I'm going to actually expand it. This will give me d a d phi dx dx. Yeah, I'm going to 5. So I'm going to expand this guy in it. This will give me d. The first term. If I expand this, if this is small, first term will be d phi and x, right? Because this one plus d phi dx d eta d, then plus the second, the higher order eta. Okay? So that's one where in GAB, I will write back my DA. DA is actually GAB. The D, dx, D, phi x, plus, here instead of using dB, I change the index to 6, because I already have B. So this d phi dx c eta c plus the second order, because this high order is our third. Okay? So this I can give me g a b d dx d phi. So this actually is the pointer here, the same as x, plus d square phi dx d dx c eta c plus d phi dx c d eta c dx d plus of purpose. Why this equals 0? is all a function of t, right? Doesn't depend on x, y, z. So that's why this equals 0. Remember, we consider two lines. This is my eta at, right? This is x at. So this guy's does not depend on x, y, z. Depend on difference. So this actually equals 0. Then I get actually dA, G, AB, D5, dx, D, and point P plus G, AB, D squared plus dx, D, dx, C, eta C plus. Correct? So this is a partial derivative. One certain time is a curve. If this is a curve derivative, I cannot change over, right? You already know the Riemann geometry. But here, partial derivatives, we can change it over. So I can still write this. This is like like what my notation. This is dA phi P plus. This will be GAB. I write this D dx C D dx D phi eta C plus all E squared. Right? The reason why I do so because the following. So you see now this is partial derivative. Remember, this one is either equal 0 or 1, right? So I can take these sides. Correct? So then I have actually dA phi and point P plus eta C D dx C G A B D phi dx D. Right? Because it's comes. This will allow me. So dA phi P plus eta C. This actually like what this actually equal dA phi. So this actually dC dA phi and from P plus O eta squared. Okay, so I just simply write this form. Now, if remember we have actually x double A equal minus dA phi and P x double A plus eta double A equal minus dA phi and from Q. So this actually the double this dA phi and the point P. I'm going to dA phi and the point P equal this. Right? This is what we get. So I just substitute here to this expression. Then you can see this will equal minus dA phi and the point P and minus eta C dC dA phi. So I just threw the second order. This guy's cancel with this one, correct? I get this equal minus. So all I have, I'll get the following. C, D, C, D, A, right. This is both sides for the P, so I just symbol as right. So this is my geodesic derivations in your 27. So now if I introduce what I did here first, I just load this index. I just like change. This always you can change part of the work. You can change all of these. This I can see. This A, alpha A, from here actually I simply change the right. Okay. This actually is the two equal. The only looks like good. Right? Any question about this part? So I just cycle through the cycle of how each. So that's right here. See here, because this actually cut AB, so if I cut A equal B, then one index up, one index down means a sum. So this becomes Laplace operator. So this is actually equal cut AA equals. Okay? So this actually is the Newtonian equation. We just simply change the notice and use cut. But you are more familiar with this. So why I write this? Because I'm going to actually compare this one with Einstein's with a Riemann geometry. So ever you heard the story, Gravitational was Einstein's classmate. Gravitational recommended Einstein to the Riemann geometry to Einstein. This is where the pure mathematical part I'm going to introduce. Next is the geodesic division equations. Like what I just mentioned, why we want to do this? Because we will frequently use this part, even later. Okay? So before we go to the next, any question on this part? Okay, good. So I'm going to actually use this actually is a rhythm geometry, geometrical relations. So what we do is we consider then we know this is the test particles will move along geometric timeline. Timeline geodesic. So this means that, for example, this is x a equal, let's say, tau. We use proper time. Okay? So tau is the proper time. Now our a will equal 0, 1, 2, 3. So this actually, you can simply write now xa equal t x y z. But now we remember instead of 1, 2, 3 equal 0. Okay? So this actually the proper time, actually the d x a d tau. This is the proper time. So we call this velocity wave. Okay? The time is like wave. So now in order to compare with this one with this actually, we need to consider second test particle nearby. So the second test particles, if nearby this one, I'm going to actually simply write here, there's this actually C1, this is C2, right? So here actually this guy is covered with a tau. Now what's happening with this one? I'm going to use nu to distinguish from C1, C2, right? So for example, this actually will be nu1, this will be nu2. So now you can say, I have actually a common growth of geodesics. Now this actually xa will equal xa tau nu. So that whether the same nu, which means I will consider one single geodesic, right? So if I have same tau but with a different the nu, this actually I'm considering the geodesic 2. So nu to tell us if you are pulling particle 1 or particle 2, right? So I'm going to introduce the two parameters. One is the nu characterizes different geodesics. Tau, actually, the proper time are H geodesics, right? So then you can see I will have like form a network. So two-dimensional, right? Tau and nu. So one nu is very small, which means I'm considered two nearby geodesics, correct? So then you can see the continuity vector for fixed nu. I have actually now my V A equal D X A tau mu D X D tau. So this actually is the continuity directions. But the really different nu means I'm considering different continuity directions of the geodesic, right? So I can also introduce another quantity I call psi. This actually will tell us dx a d nu. So this actually psi, right? Psi means actually the vectors with a fixed tau, because the positive vector, the same tau. So let's see, here is the the P1, this P1, but they have same tau, a different geodesic. So this anchor, the deviation between the two geodesics, right? So I have, just remember, this anchor, the tangent direction along a fixed geodesic. This side, there's a matter deviation between two nearby geodesics. Let's call it C1, C2, because this angle dxa dv, correct? So please do not get confused because later we'll use this one. So we have this one. Now you also know, let's see, dxa dxp. So I can write this G A B D X A D tau because I'm ancient geodesics. I'm considered around geodesics. So now if it's better to use Hush derivative since this is around one fixed geodesic. So this should be D tau dx D tau D tau. This angle gives me G A B D X A D tau. So this will be my way A. This will be way B, right? So this P tau squared. Then I have G A B way B equal ds d tau squared equal, this is what I want to prove, right? So on time geodesics, I have way A equal 1 minus way A equal G A B with B, correct? So this accurate part I would like you to remember when we use this expressions. This expression called equations. This will be our first equation. This comes from, okay, yeah. Any question about this part? So we have this one. Now I'm going to derive some relation because we will use this. So you will get confused definitely, but later you will say, okay, this is very simple. First remember this one, okay? So let's first consider the covariant derivatives around set integers. So what I do will this actually way A. By definition, if you remember correctly, this actually equal set B delta B way A way B. So this is the meaning of this is the called direction current derivative on set B derivatives. Correct? So this actually will equal set B delta B with A with B plus with A. So this will be A, right? This will be A plus with A delta B with, correct? So this actually, this equal 2 times set B delta B with A with A. Now why? Because this actually give me, this is called G. I can use G log this one and put a G here. So this actually is equal, exactly. Correct? Any question about this part? Yeah, okay. But this guy's equal 1, like what we said, right? A constant that scalar, the current derivative equal part of the derivative. Part of the derivative, a constant equals 0. Correct? So this anchor, you see, if I have a C, this will be equal, say, B, derivative B, C, this is equal, say, B, D, C, D, X, D. Of course, this equals 0. Part of the derivative is current. It's always the case, right? So this angle equals 0. This equals 0. We have the following. Right here. So set B, this angle equals 0, because 2 we can get throw this one, which means side E, V, A equals 0. I can also write this way, A. This angle again, by definition, is direct, it's a director, right? So this angle will be our first equation we need. I can simply also write this like V A side V A equals 0. Because I just write this by G mu mu and allow this by G mu mu. This guy said G mu mu and current are like constant. So this angle is the same. I just simply write all this. Any question on this part? Okay. So I'm going to derive another one. The derivative is the delta V A equals 0. So this equal V, that's B delta B V A. By definition, this V equal dx A d tau, and here, this is actually V A dx V A. I'm going to write here. Oh, sorry. This actually, by definition, this actually will dx d V A plus gamma A B C dx C d tau. Correct? This is the current derivative of this part. So I just write this one and this one. So this actually will dx A d tau plus d dx d. This again, this will be d x A d tau, right? 9 plus gamma A B C dx C d tau. Now I'm using here. You see x let's restrict. So this should be B, right? So I need your help here. So this angle is B, right? Because this is B will be. Here is A. So this angle D, this is channel, right? This angle give me D tau, dx A, d tau, correct? Here, A is the channel. This angle plus gamma A, B, C, dx D, d tau, dx C, d tau. This is equal D squared x A, d tau squared plus gamma A, B, C, dx d d tau dx c d tau. This is your list equation, right? So this is equal to 0. I'm using a pi parameterized. So which means this guy is equal to 0. Then you actually are for mu. So we have actually the formula for lucid. So I'm going to write here. So V A equals 0. Then we get another one. So this actually V A equals 0. We also get delta V. So this actually, so far we got this actually just because this we consider geodesics. So any questions so far about this part? Okay, very good. This oh, sorry, you're right. This timeline, okay, yeah. This timeline, this one, this, okay. And the mystics. So I'm really need help, so this so we have this one. Now we also want to see the this need the word. This equal by definition is equal VB DB say A minus say DB right? This is a lead word. This who wants to say what's this? The definition of this guy is dx d d tau and dx b. This means dx b, right? Then this guy is equal dx a d d right? So this is the definition. Then minus dx a dx. This is b d new. This one is dx b. By definition, this is x a d tau, correct? Now I'm going to use the channel again. This is equal d squared x a d tau d nu. This is minus this again channel to d squared x a d nu d tau. Like what we said, the partial derivative always commute, right? So this angle equals 0. So which means this angle guy is equal to 0. So if this equals 0, now this equals 0. I'm going to replace covariant derivative, partial derivative by covariant derivative. What you can see, let's see, here we A delta B say minus say B delta B with A. This is by definition you can see now it's called V A say A B. This is a positive derivative, right? Plus gamma A B C say C. This is the first part, right? This is actually the current derivative minus say D with A B plus gamma A B C with C. Correct? So then you can see this will equal V A say and I do something. This will be RA. This will be, this is going to be with B, right? You see here, B, B, this B, B. This is like a with B, sorry. So this item will be with B, sub A, B, plus gamma A, B, C, with B, C. Minus, so B, with A, B minus gamma A, B, C, so B with C, right? This is two-term cancel, right? Because I just, this guy is coming. So remember, this is gamma A, B, C equals gamma A, C, B. So using this array, so you can, this two, then this angle will give me with B, so A, B minus, so B with A, B. So this is exactly this one, right? So they are equal, which means this guy is equal to this one, right? So I get another relation. V, B, so A equal, so B, B, correct? So this actually was a way, we have this actual relations. This I can also write this like delta V psi A equal delta psi V, right? This is the same thing. It is the direction. Correct? So I'm like to play some mathematical games here. If this is a case, then both sides, I can always take delta V psi. This will always equal delta V psi V, right? So the same because this is equal, I can get this. So I'm beginning to occur in the little mind. I will erase here, and I put this relation here. Delta V, so equal delta V, psi V. This occur, the identities I can derive from what do we start here? Any question on this part? Okay. So you guys were good with the mathematics. I think that's why I like what I said, I have 7 grade students, 2 of them from India. So I like actually student here. So we're good in mathematics. So this anchor relations, now I'm using one identity. which I will not prove. You can usually use the definition of a linear relative to do the following. So this actually delta x delta y za minus delta y delta x za minus delta x y they equal R A B C D Z B X C Y D. So this is the identities you can prove. So here, this actually the lead. This guy is the leading representative right there. So you can find this. This is for any vector x. This vector x equal, let's see, x a b y equal y a b This is my definition, right? X or y. So this, you can use this. So this is for any x or y. I'm going to actually put in, if I consider x, a, setting x, a equals z, a equals v, y, a equals. So, because this is true for any vectors x, y, z. I simply put x equals z and y equals z, right? So if I do this actually, let's call this equation 1. I think I already have 1. If you don't mind, put 2. Then we put this actually, do this, then you can write this actually equation 1 in the following form. This line is about 0 right here. This the geodesics. This actually equals 0. Now this guy, remember, this is equal. This one's the lead relative, right? So this actually equals 0. Because this guy is 0. The lead relative. Remember this equation we get it from lead relative. So now I simply have this equals 0. Now I'm actually delta v delta psi v, and I also have this delta v delta psi v equal this, correct? So this actually equals delta v So this actually equal one side. This another side here you can see equal R A B C D. Now Z equal V, S equal V. So V B V C side D. Correct? All right, guys. Delta V side A equal R C. So this is my third equation. You see here, those are actually a basic equation. We can easily use this identity to get this actually called geodesic equation. Why this? I'm going to write it down. Let's say first one, what's this one? About definition, right? This are also equal d tau psi, correct? This is called observability, right? Because I'm taking this geodesics. This is observability relative are my geodesics. That's actually the parameter called tau, right? This is two equal. Then you can see the same thing way, delta way say for equal delta way d say d tau, this will be d tau d say d tau. Perfect, right? I get this one. All I have, then you can say equation is d squared, say d tau squared equal r a c. Say D with C. So this is called geodesic deviations. Geodesic deviations, you can see the nothing more than the acceleration between two geodesics, right? So this is actually the deviation vector. This is actually characterize the difference between two nearby geodesics, right? So the second derivatives give us acceleration. So acceleration connect with the forces, right? So that's why this guy is important. You see here, the Riemann tensor. Right? Like what we emphasized at the beginning, here when we see no geometry is no curvature, right? So this actually, now we have a curvature term appears. Any questions so far about this part? Okay. So this actually out the medium of say. So we have a C1, we have C2. This is a network. So this actually say, yeah, this actually the way actually, this is called way. That's Q is a way and P, right? But this two vectors here is a way, they are not necessarily 90 degrees, right? What I'm going to do actually, I will introduce another vector here. I call zeta. This will exactly 90 degrees. I'm going to write this one. Instead of zeta, I will actually write the eta. Remember in Newtonian theory, we use eta as two geodesics on x-ray direction. Actually, direction, they're actually 90 degrees. We want to do something similar. So, our goal is, this is a geodesic device. This is a side connect to nearby geodesics. But now we want to write geodesic device in terms of eta, where eta eta equals 0. Why? Because V psi in general is not 0. Okay? Because we just simply use, by definition, this is not, but this, we are going to use this one. We write this geodesic devices in terms of eta. You will also take the same form. So this next step, we are going to prove this. Okay? The mathematical proof is complicated. Sometimes like this may stop, I need your help. Because there's something wrong, so let me know. You just have to remind me this is 0, it's not 0, because your time, right? So you will see actually, you put a 0, the equation remains the same. Which means that we're considering non-geodesics, right? Large geodesics. So when I define the probability of rotational motion, I use non-geodesics. So you will see it will be the same. Either way you can find, you can define the probabilities. Okay? So to introduce these vectors, we just first the vector on projection operator. So this actually called HAB. Sometimes we use the PAB. Here I use HAB. In this course later we'll use HAB as a weak gravitational field. Yeah.
The particles or which particles exactly?
This actually now is actually the top. We just fix that. That's around C1. Yeah, this is actually C1 first. The top. You can see all of the C2 because they're nearby. Right? Yeah. I just use one parameter as top. Okay. Yeah. Good. Any other questions? So this actually, now we'll introduce this guy, simply delta AB. So delta AB is currently called delta function minus VA, VB. Or you can write it as HAB equals GAB minus VA, VB. The same thing. Now remember, this guy, the GAB is a curve, the measure. The split time is going to be n, right? So not a natural eta. So we introduce this famous project operator. Then you can see we define actually eta A, H, A, B, set B. So this actually, you see now, I first introduce one projection operator. This is equal either AB minus VAB, or you can use one index up or another index down. This actually the case. So then I define eta AB equal HAB. This one. Okay, yeah. On eta, this is exactly because the eta, you see, this is the orthogonal way. Yeah, this is giving me actually the 90 degrees. Eta, the very good qualities to actually is perpendicular to the tangential vector of geodetic. Yeah, this is all right. But mathematically here, so far we just do the mathematics. Okay. Yeah. Good. Any other question? You see, once I define this one, I'm going to prove this guy exactly orthogonal way. This is what I want. So this actually, this will be equal delta AB set B minus VA VB set B, right? By definition. Then you can see now eta A VA will equal delta AB set B VA minus VA VB set B, right? This equal 1 here, correct? So this equal 1. This is only B equal A, this equal 0, otherwise equal 0. I have set A V A minus V B set B. So this equals 0, right? This is exactly the property we want, correct? So I just want to introduce this guy, we get that one. Okay? So if this actually equal 0, this actually I will risk here. So we indeed have this problem. I will not prove, just prove. Now I want to write this. This is equal, like what I said, this is equal, say, minus, sorry. What am I doing? Actually, oh yeah. Will be 7, right? I'm going to actually take this on our side, get a say from the eta. Then I will park here. Oh, I have say equal eta A plus VB set B, right? This is what I get from the definitions. Now I want to see D say eta equal. D say eta equal D eta A eta plus D eta tau with A with B set B, correct? Because this thing, so by definition, this are also equal V C delta C with A with B set B, correct? This is the direction. So this angle will equal delta V A with B set B. I'm going to apply this one. This will be 0, this will be also 0, right? So I directly have the following.
So can I take 1 minute?
Yeah.
In the certificate, if you want doctor.
Fine. So today actually this class will be very boring because we are doing pure mathematics. Okay? But I don't want to follow you because we need this part. So we get that line, you can see this angle equal, like what I said, this is equal VA, VB, delta V, set, right? So because this line, delta VA here equals 0, then delta VB, you can log in next, it's also 0. Then I have VB, delta V, set B, right? So I have this. So now you can see I'm going to use this guy. VB, see here, this will be VB, VA, right? Why I have 2 index down. Okay, yeah, we decide. What's that? This will be P. So, correct? Here. Say B, wait, B. What I'm going to use in one more actually, this guy. Delta VB. Use this should be d eta a d tau plus this one, right? I have it here. Here, then plus this one, right? So I have d eta. The program is plus d eta a d tau. So this guy is actually here, where when I want to see this part, this will be 0. So why I want to see this 0, this actually way A, this way A, so will be here, right? Way A. This will be wave B, wave A here. So wave B, right? So now this 2 here will be 0, right? This will be, let's say, wave A. Wave B. Why? Because this actually equals 0. Correct? This is 0. So this actually equals 0. Then I have this is d theta d tau actually equal d eta. This is what I want. Correct? So this actually, this equals 0, this actually will be this part. So I prove this equals 0, and I get this one. Correct? Any question on this part? Yeah. So this, if this is the case, then you can say, okay, I'm simply replace this guy by eta. Okay, take the second derivatives, this will be d squared, theta d squared eta d tau squared. So once I get that one, I'm going to have actually d squared eta d tau squared equal r a b c d v c. Remember, we always change this eta psi d the equal d plus v d v e c. Correct? I think by definition, this is eta, this is psi d. Psi d equal eta d plus v d plus v. I just use e. So this actually equal r a b c d v d v c e d plus r a b c d v d v c v d v e psi e. This is a way CD, right? Here CD. This guy is symmetric, right? This side is symmetric. This equals 0. Okay? So I just simply equal R A C D V D V C E D. Okay? So finally we get this one. You see this actually, you just simply replace psi by eta, you get the same geodetic relations. But I already do the same actually the following. So we introduce eta A equal delta A D set B, then we get actually D squares eta A D tau squares equal R A B C D V B V C eta D. So this angle will be another equation, let's call 4.0. They are equal. Okay. Why this one, like what I said, this actually has good properties. They are solid. This is a tangential direction around my geodesic. This is an exact perpendicular to my tangential direction. Why? Because it forms two legs of one tetrahedron. Okay. This is important later when we project a Riemann tensor into a tetrahedron. Remember the components of a Riemann tensor does not have very physical interpretation unless you have a physical tetrahedron free. When you project the Riemann tensor to this frame, then the components has physical meaning. For example, if I consider the geodesics, I will build a free fading frame or power transporting frame. That actually the geodesic, time like the geodesics, the particles carry one frame. That frame is not rotating. This is called power transported. Did you learn this part? If you do not, no problem. That means that this is foreign, this is foreign geodetic like this one. It's not rotating. Why this is important? Imagine if I define a polarization in terms of this frame. If your frame is changing with the time, that angle has no meaning, right? So if I define a frame as a power transported over a frame, the same thing, that angle has the fixed meaning. Okay. This is exactly I did in 1991. The introduction for defining powers angle on this one. Then the polarization has a physical meaning. Otherwise, the angle you define depends on which kind of texture you consider, right? So it's difficult to talk about polarizations. Okay? So this is actually another one is why we pick this one to try to answer your question. But so far, pure mathematics. All we're going to say this guy is orthogonal. This is a tangential direction. Okay? Yeah. So this is exactly what I'm going to say the physical meaning. Now I'm going to come back to the geodesics.
So can you explain what a tetra is?
I'm sorry?
Can you explain what a tetra is?
The tetra? Yeah, tetra. Tetra means like four orthogonal vectors. Okay. No problem. Sorry, if you actually have any difficulty to understand, just ask me. Okay, I'm waiting. So, thank you. Okay, yeah. Any other question? Okay. Not only my English, even my handwriting asking me.
Can you please repeat why this that term goes to zero?
Oh, okay. Because remember R, A, B, C, D equal minus R, A, B, D, C, right? Yeah. So now if I use this one, okay. So the first part will be until trade. Oh, let me see. Perhaps I can stop here. This is exactly my section. Otherwise, we will pick up the next time.
Yeah, no problem.
Okay?
Yeah.
Yeah. Because I have only 3 minutes. This is exactly you can see in my notes in the next section. So let's go to the next section. Okay. Okay. So this is like the next time I will introduce the tetra.
Yeah, great.
And then it's just over time. Okay.
Thank you.
Yeah.
Thank you. Proceed with the quickly. 9:30 sharp.
Okay. Good.